this class, we'll have a brief overview about how modern sensors are being designed, how they are used, and in what areas they are being utilized. And we'll also see how electronics can be used to pick up the signals from these sensors and to process it. So we'll have a couple of examples to demonstrate the concepts. In case you have questions, you can ask me at the end of these slides. So when we talk about the sensor, basically we have to talk about a transducer. And what we mean by transducer is that it's a device that converts one form of energy into another form. So let's say we have some energy, some quantity, physical quantity such as force, pressure, etc. We want to convert it into an electrical form. So there are two types of transducer. Both are called as transducer. One is called actuators and one is called as sensor. So today's slides will focus on the topic sensors, where I will explain you how different sensors based on these techniques such as capacitive, piezoresistive, resonant, piezoelectric, optical are used. And remember, there are many other techniques which we can use to design and develop a sensor. So let's understand little bit of physics of these devices which are used as a sensors, because it's a electromechanical device or it's a optical mechanical device. So there are a lot of different domains that are involved in the sensor. So for example, a transducer or a sensor can be modeled as simple mass spring damper system. As you can see here, there is a mass, it is connected with a spring, and there is a damper. And when we apply a force, it could be a simple mechanical force, this mass gets displaced from its original position. This mass will move. If we have an alternating force in nature, so it will start vibrating as shown here with the animation. So you can see here that the net force acting on the mass is given by this very famous equation, F equal to mass times acceleration. So we know that acceleration, velocity and displacement. Acceleration is the rate of change of velocity with respect to time, and velocity is the rate of change of displacement with respect to time. And once we know that, we can simply sum these forces and see that summation of these forces is again mass times acceleration. So this is the simple second order differential equation, where we can see that this Fe is the force acting on the mass, which is our externally applied force. And due to that, the displacement is happening. Then we have second force, which is due to this damper, which is called as Fc and is given by velocity times the damping coefficient. And the third force here is K times X, which is the force offered by the spring. So whenever the mass due to external force comes down, the spring will try to pull it up. This is called as restoring force. So basically, when we talk about designing or understanding a sensor, what we see here is that there is a transduction happening, which is converting one form of energy into another form. So what we can say that, for example, these are the quantities in the mechanical domain, such as force, velocity, motion, spring, mass and damper. And they can be converted into equivalent quantities into electrical domains such as voltage, current, charge, capacitance, inductance and resistance. So when we talk about sensor, can we represent that into electrical domain? Yes, using some circuit. So you see here, this is the second order differential equations in the mechanical domain, which is same as this equation, which says that external force is equal to mass times acceleration plus damping coefficient times the velocity plus spring constant times the displacement. This is the mechanical domain representation of this sensor. How about its electrical equivalent? We can have this RLC circuit as shown right over here, which can mimic the behavior of this transducer or sensor in the mechanical domain. So what we see here is that here is the input side, we apply electrical signal. This transformer will model the energy conversion from input side to the input side. So what will it do? It will model the applied electrical signal and convert it to equivalent applied force onto this mechanical structure. And then this structure, because of the alternating force that we have applied, it will start vibrating. So how to show the vibration? We know that RLC is an electrical network that has a resonance. So that's why we have used this RLC component. What is the output of the mechanical circuit here? Is the velocity, because it's in the motion. So that velocity can be converted back to electrical domain by using another transducer model. So here is the transformer that is modeling the energy conversion again back from mechanical domain to the electrical domain. So the output will be the current, and that is how we can see that how we can understand the mapping between mechanical domain and the electrical domain to understand the behavior of a transducer. So here are different modern sensing techniques that is being utilized. There are governing equations that needs to be understood, but in today's session we'll just focus on the working principle, and as we extend our lecture we will detail one by one, take these techniques one at a time, and we'll also through governing equation case studies will explain them in detail. So have a look at this. This is basically first technique called as capacitive sensing. So what we have here is that a simple parallel plate capacitor. We have a top plate, we have a bottom plate, and arrangement of this transducer or sensor is such that bottom plate is fixed and top plate is hanged with a spring to some frame. So when I apply an electrical signal to the top plate with respect to ground, we already know that from the 12th and 11th class physics, we have a creation of attractive electrostatic force between the two plates of the capacitor, because top plate is positively charged. Because of this force, this top plate will move a small distance as indicated by a green line, and we say that the top plate has been moved by a small distance, and now the original capacitance, which was epsilon A over D, is now become epsilon A over D minus X. So we see that distance decreases, capacitance increases. So we can take this plate up and down, and accordingly we have delta C. So we have change in displacement that will get converted into change in capacitance. Once we know, we can have electrical circuit to convert this change in capacitance into equivalent voltage or equivalent current, and accordingly we can measure how much change has been occurred. So this is the first example. Second example, as we know that we have already seen the piezoelectric crystals. We can see them from the market. We see that widely used in several of applications. So here we see that a quartz. What is the structure of this quartz is very simple. It's basically two electrodes supported by the base in the bottom. This is the base, and the greens are the electrodes, and in between those electrodes there is a very thin layer of piezoelectric material. So based on the piezoelectric material, its type, its property, its geometry, its structure, the performance of this transducer will be happening. So let's see how this will work as a sensor. So what happens is that when we apply a voltage difference between the top and the bottom electrode, there is a creation of electric charge of opposite polarities as indicated here. We see that positive charges and negative charges. So when we applied the mechanical force, let's say we press this material and the charges are produced. So again, we can use this charge to voltage conversion by means of electronic circuit. Where is the direction of motion? Because the material is supported with the bottom plate like this, the motion is indicated by the arrow. In this structure, the base is supported here and it is simply a cantilever. So once we apply force, the charges will be created and the motion will be in this direction, because this is the maximum displacement point and this is the minimum displacement point. So how to sense the signal out of it? Once we have this charges creation, as I said, we can use a charge amplifier to convert these equivalent charges back to the voltage. There are some other examples also here. We can explain them in detail when we specifically understand the piezoelectric sensors. Let us move to the third and very popular sensing technique. We know that semiconductor materials such as silicon and germanium, they can be a good piezoresistive material because they offer this piezoresistive property. What does that mean? When there is a strain or stress in these kind of materials such as silicon, they experience a change in electrical resistance. So how to use this property to design a sensor? So what we do again, this is a simple cantilever as you can see here. This is a base. It could be a silicon. Then on top of that, people with the manufacturing process and the industry people, they use the fabrication technique to deposit a piezoresistive material. Let's say there is a polysilicon over here. So that is embedded at this point of the structure. And then there is a wire for the connection. So there are two ways to sense the signal out of this sensor. How? Let's say on the top of this silicon we apply force here. So as I explained, this will move down. So we have two ways. Place a bottom electrode. So you see here we have a parallel plate capacitor. So when the top plate moves down, we have a change in capacitance. Okay, so it becomes our capacitive sensor. What if we don't want that? We want to change to sense the change in resistance. So as I said, when this silicon cantilever moves down by a distance x, the maximum displacement point is here, but the maximum strain is created at the base, and therefore this resistor, piezo resistor such as polysilicon, has been deposited here. So once the cantilever bends down, there is a maximum strain occur in this area, and because the resistor is placed there, this resistor will experience a maximum change in its value. And once we have that, we have simple electronic configuration. We already know that this is a Wheatstone bridge. What we can do is that one arm of this bridge is our sensor. So this sensor has been placed in this arm. So when the bridge is balanced, here is a DC voltage, let's say. When the bridge is completely balanced, the voltage difference between these 2 points is 0 in ideal conditions. Assuming there is no temperature effect, there is no pressure effect, there is no surrounding effect such as vibration. And when resistor undergoes a change because of the applied force or applied any quantity, let's say pressure or whatever, so what we have, we see a voltage difference will be generated, and that voltage difference can be correlated to the resistance change, and the resistance change can be correlated to the motion. So this is how you see these techniques are being used to design a very precise, accurate and stable sensors using modern IC design techniques. There are some other fabrication techniques also and technologies available, but that's not our focus. Our focus in this session is to just give you a basic understanding about how sensing techniques are used in modern sensors. Here is another example. We can see that let's say we want to measure an applied air pressure, ambient pressure. So here is our sensor structure, here is our base, let's say it could be a silicon, and you see that this is a very thin membrane. So it's just like a diaphragm in your loudspeaker. So there is a diaphragm, and on side portions of this diaphragm there is a embedded resistors. And also if we are interested in capacitive sensing also, we also design and fabricate a bottom electrode here. So when there is a pressure, this membrane will bend down, up and down depending on the applied force, and it will experience change also both in capacitance and in the resistance, and that's how the sensors can be designed. So you see that I explained you the capacitive sensing technique, I explained you the piezoelectric sensing technique, I also told you about a piezoresistive sensing technique. But you see that this is a complete transducer. It means actuation and sensing is happening in the same structure. So as I explained here, transducer is also actuator and also sensor. So when we apply any external force, or any external signal comes here, it could be a biological signal, for example molecules in the air, some gas vapors, they can get deposited on top of this material. So this cantilever has a effective mass, let's say few nanograms. So when those molecules will be deposited on top of this, its effective mass will change from, let's say, 1 nanogram to 2 nanogram, right? So what we see is that its mass has been changed. Because of that mass change, the cantilever will bend down by a little amount, let's say few micron, and therefore there will be a change in the resistance, there will be a change in capacitance. So you see very precisely, nowadays we are able to detect a very small quantities. Okay, moving on to the next transduction principle. We have two materials, for example material A and material B, and they are different geometry, they have different temperature properties, because we are talking about thermal sensors. Here is a base, and in between these two material there is a thin layer of other materials. Let's say it's a platinum, and we call it as an embedded heater. So when the current is passed through this structure, this embedded heater will generate heat that will transfer to both this material A and material B, which has different TCE, which is, we know from our elementary physics that TCE stands for temperature coefficient of material. So, excuse me.
Dr. Vinayak?
Yeah.
We have quite a bit exceeded the 15 minutes that we were expecting this lecture to be. So if you can please wrap up in 1 minute.
Right. So because of that temperature difference, this structure will experience the bending moment, and that becomes our sensing. And therefore, this is how we can actually explain the working of a thermal sensor. So we stop here now because we have exceeded time, and we'll continue our discussion in the next session. Thank you.
Right?
Yeah, thank you.
Any questions from anyone?
A couple of questions from my side. Hello, Dr. Vinayak. This is Dr. Bhargav. So one question is, say, for example, if I'm measuring temperature, say, I've seen multiple ways in which you measure temperature, right? So you have an IR thermometer, you can use a thermocouple, you can use a thermistor. So I'm an embedded systems person, right? So from an embedded systems perspective, so which sensor would be preferable to measure a particular quantity? Physical quantity, because you have multiple ways to measure the same thing. How would you differentiate between them in terms of which one is preferable?
Yeah, thank you, Bhargav, for asking this question. So basically, in one of the topic, I have explained this resistor temperature detector. I have prepared the slides for that, thermometer and the thermocouple. These are three widely used temperature detectors in industry, in home automations. So RTD is very commonly, and the most precise is the thermocouple. They are, as you rightly pointed out, widely used for embedded applications.
Okay, no, actually there are more than that. So what I was expecting was there are characteristics to each sensor, based on the range it can sense, based on the voltage signals it can provide, the signal condition required, the precision, accuracy. Also, there's one thing. So there are two things that I've always seen with sensors: precision and accuracy. Can you tell me what the difference between the two are?
Right. So precision and accuracy of a sensor. Precision means how precisely it can measure a particular quantity. For example, we want to measure a very small quantity, very concentration of some molecules. For in the case of temperature sensor, when we talk about precision of a temperature sensor, means how precisely it can measure that temperature. And accuracy means, let's say it can give me a temperature reading of 2 degree accuracy. It can give me a temperature reading of 0.1 degree accuracy. So I will say 0.1 degree accuracy sensor is better for me.
Okay. Last, one or two questions if I have the time, Ram, or else you guys can take over, and if there's time left, I'll come back with a couple of questions.
Sure, go ahead.
Okay. So you mentioned this beadstone bridge configuration here for measuring resistances. So typically, when we have lesser components at hand, we just go for a potential divider instead of a Wheatstone bridge. Right? So can you tell me what the advantage of using a Wheatstone bridge over just a potential divider? For example, the same R sensor can be just used in series with another known resistance, and you just have the voltage division there. So voltage divider, and then you measure the voltage across your sensor and say, okay, the voltage varies with respect to the physical quantity. So what is the major advantage of the Wheatstone bridge for measuring change in resistance as compared to a general potential divider?
Right, right. So, when I was explaining this part of the Wheatstone Bridge, I briefly mentioned in one sentence the advantage of Wheatstone Bridge is that the reading will be insensitive to the temperature and let's say pressure changes, because in Wheatstone Bridge configuration, all the resistances they are in this configuration, in the bridge configuration, they experience the same changes in their values due to let's say temperature change. So there will be a combined effect on the output to voltage difference will be zero, the net effect will be zero. But in case of simple potential divider, if the resistance changes due to let's say temperature, the output is varying with respect to temperature.
But typically, when we look at sensors and calibrate sensors, we also calibrate with respect to the ambient conditions, is it not?
That's, I think, in my understanding, that's a different part. Calibration is different part. But to answer your question with respect, let's say due to temperature, we don't want output voltage to be varied. We are measuring the temperature of a quantity, not the ambient temperature. So let's say I measure the temperature. I measure the temperature at 27 °C, and now the ambient condition changes to 40 degrees Celsius, so the voltage difference will be different, so I again need to calibrate. In Wheatstone bridge I don't need to calibrate that.
And last question, you had mentioned in one of the earlier slides how you are converting these mechanical quantities into several different electrical quantities, right? R, L, C, voltage, current, charge. I think, yeah, so yeah, over here. But I don't know, when I use microcontrollers, I always only see voltage. There's no way to measure current with a microcontroller. There's no way to measure capacitance. There's no way to measure inductance or resistance. So how does it work there then? So because I only measure voltages using an ADC. You have an analog to digital converter, it only takes the voltage as its input values. So how does it work in that case when, why do I have to consider all of these different conversions in that case?
Right. So in this particular case, we are talking about vibratory sensor. So we are basically not measuring the voltage or resistance or current. Rather, we are measuring the frequency of a signal, which is also very precise output these days. So for the frequency, I think we can use simple frequency counter. We can also utilize microcontroller
No, yeah, true that. I mean, frequency is one thing, but you have mentioned these have several different parameters which change, right? So, for example, our most common measurement is the resistance or a capacitance. So, a lot of your MEMS accelerometers, all are capacitance based. Even the sensor that you had presented during your research seminar was capacitance based. But I cannot directly measure any capacitance with the microcontroller. How do I measure these things with the microcontroller? How do I
Yes,
disguise them?
yes. Thank you. Yeah, yeah. Eventually, we have this complete embedded system where sensor, electronics are all integrated and sitting on top of PCB, and we have this microcontroller. So, what we have is that let's say we are measuring a physical quantity, and the output is the digital reading. So, capacitance coming from the sensor changes is getting converted into equivalent voltage. That analog values are being getting converted with A to D converter, which could be in inbuilt part of a microcontroller or it could be outside the microcontroller. And we have digital codes that is being converted and correlated with the input quantity. Yes, you're right. Is that answer to your
Thank
question?
you, Dr. Vinayak. Ram, I'm done with my questions. Thank you.
Okay. Thank you, Bhargav. Anyone else have any other question?
Just a couple of questions from me. Hi, Vinayak. Aditya here.
Hello, Aditya.
So when we talk about sensor characteristics, they basically you have your static characteristics and your dynamic characteristics, right? Can you just elaborate a little bit about that if you are aware of that?
Yes, Dr. Aditya, thank you for asking this question. So let's say this is the simple example, we have this physical model of a transducer. If I apply a static force, let's say with the hand I pull this mass, it moves by a distance from its equilibrium position. And as I explained in other
No,
slides.
forget no. So forget a mechanical sensor. Pick any electrical sensor, right? For example, say gas detector or something like that, right? Any kind of sensor for that matter will have both a static characteristic and a dynamic characteristic. So, are you aware of that? Any idea what the static characteristics are and what the dynamic characteristics are?
For the electrical domain, I'll have to just recall back. Currently, I'm not able to recall that. Yeah.
That's fine. So dynamic is basically your frequency response, impulse response. Those are your dynamic characteristics. But going back to the static characteristics, there are a couple of characteristics which are generally not looked at when you look at some publications, or they're not talked about so much. But non-linearity is one of the major characteristics. Can you explain what non-linearity is in a sensor?
Right.
Could you hear me?
Yeah, yeah. You asked me about non-linearity of
Yeah.
a sensor. Right. So,
Correct.
yeah. So, I mean, in my understanding, when we talk about non-linearity in the sensor, is the percentage change, percentage deviation in the sensor output from its linear curve. So on the y-axis we have output of a sensor, and the x-axis we have, let's say, input quantity being measured. So what we expect is the linear behavior starting from the origin, but when we have a deviation, and that deviation we measure in percentage, that we defined as a non-linearity.
Okay, and when you design a sensor or you fabricate a new sensor, how do you look at this particular characteristic of nonlinearity as part of the design? So, do you understand what I'm trying to
Right,
ask?
right. So when we measure the characteristics of this sensor, let's say we designed and fabricated one prototype, we bring it to our lab, we make a test bench, and when we are actually recording our output reading, so we have those output reading with respect to our input quantity. So when we have a graph, as I just mentioned, we should see a linear curve, linear shifts in the output with respect to the input. So when we have a deviation from that, we then calculate in percentage how much is the non-linearity. This is how I understand. This is how I have characterized my devices.
Sure. Yeah. So I think yeah, it's very close to what I was expecting. So basically, when you design or go to a new sensor, you define the amount of non-linearity that it can, actually give and still be a functional sensor. One last question about transducers. Is that fine? Transducers is also okay.
Yeah, please.
Yeah. So, any idea about LVDT and RVDT kind of transducers? If you can briefly just talk about those, if you're aware of that.
Not now. A long back, I have studied that when I studied
Oh,
instrumentation
that's fine.
subject,
No,
but not now.
correct. So when you do instrumentation, you
Yeah,
get
we
into
have
that. That's
that.
fine. No problem. Yeah, I was just curious if you were aware. Yeah, no problem. Thanks.